Hello, this is Tariqul Islam Sifat and our paper is about revisiting sparse dynamic programming for the 0-1 knapsack problem. This is the mathematical statement for the 0-1 knapsack problem. Given a set of items with associated weights and profits, we must maximize the total profit while not exceeding the given weight capacity C. Here xi is Boolean that signifies whether we put a certain item into the knapsack or not. This is an NP-hard optimization problem for solving problems like production planning, risk balancing, resource allocation, etc. The exact solution of the 0-1 knapsack problem can be found using dynamic programming or the branch and bound algorithm. But in this paper, we focus on the dynamic programming solution. A sparse KPDP or SKPDP algorithm has been known for a while. Even though the conventional KPDP algorithm generates a dynamic programming table that contains many repeated values, SKPDP does not calculate the repeated values and thus have potential to perform better than conventional KPDP. So far, there has not been any quantitative analysis of its benefits, which is the primary motivation behind this paper. So in this paper, we did a quantitative analysis of the sequential SKPDP. We explored two parallelization techniques for SKPDP and compared SKPDP with branch and bound algorithm. To cover enough of the domain of the problem, we needed a way to synthesize the problem instances. Here are four categories of problem instances. Uncorrelated problem instances have no correlation between the weights and profits of the items. Weakly correlated problem instances fall in the middle of uncorrelated and perfectly correlated problem instances. Strongly correlated problem instances are known to be the hardest problem instances. Subset sum, or in other words, the perfectly correlated problem instances, are out of the scope of this paper. With the short introduction, I can give you the punchline of this paper. If the weight capacity C is significantly larger than the number of items than for weakly correlated problem instances, the time complexity of SKPDP becomes order of n. And for strongly correlated problem instances, the time complexity of SKPDP is exponentially better than KPDP. These graphs can help visualize the punchline. For the first figure, we put the capacity on the x-axis and execution time on the y-axis on a log-log scale plot. The dotted lines represents the runtime of conventional KPDP, solid line represents the runtime of sparse KPDP algorithm. The execution time of the conventional KPDP is linear with C, which means exponential with the input size, but the execution time of sparse KPDP plateaus for larger values of weight capacity. And depending on the number of items n, it flattens out at different points. Therefore, for large values of weight capacity, the execution times of SKPDP only depends on the number of items. Please note, for this analysis, we keep the average number of items that fit into a given capacity constant by increasing the weights of the items accordingly. Otherwise, the problem instances will become trivially easy. In the figure for strongly correlated problem instances, we do not get a plateau, but we still have an exponential improvement in terms of iteration count. Here is the dynamic programming solution for the 0-1 knapsack problem. The problem is solved by building a 2D dynamic programming table And for anyone who is curious, this is the code snippet that generates the dynamic programming table. Here the K represents an item number, and the smaller case c represents a capacity value between C and capital C. Let's consider a small knapsack problem instance with 5 items and capacity of 11. Using conventional KPDP, we are going to build a table like this. The columns are ranging from 0 to maximum capacity, and there is one row for each newly introduced item into the set. In parentheses, we put the weights and profit values of each item. Now let's consider a cell with value 24. What does that particular cell tell us? It tells us that if we consider only the set of first 3 items, and if our maximum capacity is 7, then 24 is the maximum profit we can achieve. And if we look at our DP formula, to calculate this value 24, we need these 2 cells from the previous rows. Any row of this table can be calculated if the previous row is available, and each cell can be calculated independent of each other. So the calculation can be easily done in parallel. A memory efficient KPDP using divide and conquer technique has been known for a while. The idea is that we only need the current row of the DP table to calculate the next row. Storing the full table is not necessary. Even though the divide and conquer strategy doubles the number of computation, it reduces the memory footprint by a factor of n/2. Now let's talk about what we mean by sparsity. Generally, by sparse table or sparse matrix, we mean a data structure where we only store the non-zero values. This is not the kind of sparsity that we are dealing with here. Our dynamic programming table does not have a lot of cells with zeros. What we do have, however, is a lot of repeated values in monotonically increasing order. You can see the breakpoint values in highlighted cells of the table. So what we can do is just store the breakpoints as list of key value pairs where the key is the index of the column. To generate the sparse table in SKPDP, a technique called add merge kill is used. Let's consider 2 rows from the sparse data structure. How can we get from the 4th row to the 5th row? In the 4th row, we only consider the set of first 3 items. Getting from the 4th row to the 5th row means taking a new item into consideration to put into the knapsack. We first take the 4th row and add the weight and profit values of the new item to each pairs. Then we get rid of the pairs where the total weight values are higher than the capacity. Then we merge these 2 lists. When merging, we will have some pairs in one list that will dominate pairs from the other list. We kill the pairs that are dominated, and only the pairs highlighted in red make up the 5th row. Here is a graphical representation of what the add merge kill algorithm is trying to achieve. In the x-axis, we plot the weights, and in the y-axis, we plot the profits. Then we have a staircase plot like this for the 4th row. Now we add 6 and 22 to each points of the staircase. What we get is the dotted orange line. To get the 5th row, we only need to pick the maximum profit value for each values of weight. In this case, that's the green solid line. Here are some parameters that we used to generate knapsack problem instances for our analysis. One of them controls the fraction of the number of items that fit into the knapsack. We call it lambda. If lambda is set to 2, That means half of the items are expected to fit into the knapsack. We calculated the average weight of the items using the value of lambda and used a normal distribution to get different weight values. We used another parameter called sigma to control the correlation between weights and profits. For strongly correlated problem instances, sigma is not relevant. To measure the performance of sparse KPDP, we defined a term called gain using the iteration count of sparse KPDP and the iteration count of conventional KPDP. Iteration count of conventional memory efficient KPDP is always 2nc. Positive values of gain means sparse KPDP is better and negative values of gain means conventional KPDP is better. For different values of n, we see that when c is very large, we have gain close to 1, which means that sparse KPDP does significantly less amount of operations compared to KPDP for those problem instances. This is in compliance with the results you saw in the punchline. One important detail about these two plots is that the lambda and sigma values are same for all problem instances used to generate the graphs. We wanted to see how different values of sigma affected sparsity of knapsack problem instances. The higher the sigma value, the sparser the generated tables of the problem instances are, and the lower the iteration counts. Different values of lambda used to generate knapsack problem instances also have effect on the sparsity of dynamic programming table. Here, the lesser the fraction of items that fit into the knapsack, the more sparsity we have. This heat map shows the impact of lambda and sigma on the sparsity. Each block shows the peak operation count for different values of lambda and sigma. Now let's talk about the two parallelization techniques that we explored for SKPDP. Let's imagine that in this figure, each horizontal bar represents the length of the rows in a SKPDP table. The yellow rows have already been calculated, the green rows are yet to be calculated, and we are in the process of calculating the red rows. To parallelize the red row with p processors, the row is divided into p chunks. Then those p different chunks are computed parallelly. Here we are breaking dependency and we cannot just append those separately calculated chunks back together. We need to do extra merge-kill operations for each point of separation. To better explain this, let's go back to the example we presented earlier. Let's see how we calculate the fifth row from the fourth row using this parallelization technique. Let's divide the fourth row into two chunks. We apply add merge kill algorithm separately on each chunk in different threads. For stitching these two chunks back together, we synchronize the threads. Then we take at most wi pairs from the suffix of the first chunk and at most wi pairs from the prefix of the second chunk. After that, we apply merge kill on the two sections. In the worst case, we have to do wi extra operations on each point of separation. So, more threads we introduce, the more extra operations we have to do per row. Unfortunately, the overhead of the extra operations causes this parallelization technique to perform worse than the sequential version. In coarse-grained parallelization technique, we try to parallelize multiple rows instead of splitting each row. This technique works because it is not necessary to complete the calculation of a row to start calculating the next row. For this approach, each row is calculated on a separate thread. Each thread needs to maintain a minimum local buffer size of Wi. We can calculate the rows in small fixed size chunks. The chunk size and the number of threads are two very important parameters. The computation occurs in batches of p rows. Every pth row of the DP table is stored completely in the memory. Other p-1 rows only stores a minimum local buffer of size Wi. We need a buffer size of Wi at minimum for each row because to compute each key value pair, we need to look back at most Wi pairs of the previous row. The local buffer for each row are basically FIFO stacks and implemented with rotating arrays. These rotating arrays have a length of Wmax. So the extra memory requirement by the implementation is Pwmax. Unlike the fine-grained parallelization attempt, the coarse-grained implementation does show speed up over the sequential implementation of SKPDP. In the first figure, the x-axis represents weight capacity in log scale and y-axis represents execution time in log scale. The dotted lines represent sequential time and the solid line represents parallelized time. In the second figure, we have a scatter plot where the x-axis represents the weight capacity in log scale and the y-axis represents speed up. So we have speedups up to 6x on a 8-core machine. We compared SKPDP with David Pissinger's branch and bound implementation. For weakly correlated problems, existing branch and bound implementation beats SKPDP. This plot shows that even the coarse-grained parallelized SKPDP is slower than the sequential branch and bound implementation. But on strongly correlated problem instances which are known to be hardest for branch and bound, there is a wide variability in the execution time of branch and bound algorithm. On some instances of strongly correlated problems, SKPDP does perform better than branch and bound. We believe that SKPDP requires further exploration. One could produce an analytical or machine learning model to predict the performance gain by SKPDP. The order at which each item is considered may have some effect on sparsity. Also, for coarse-grained parallelization technique, the only buffer size we used was Wmax. In conclusion, a large subset of Knapsack problem instances shows exponential performance improvement using SKPDP over KPDP. Among the two parallelization techniques we explored, coarse-grained parallelization seemed to perform well. Even though SKPDP does not seem to beat branch and bound algorithm, we believe there are more avenues to explore with SKPDP. Thank you.